So our next lecture is on electric potential, and this is going to we looked at electric fields, and we've looked at the epsilon, which is how much force per unit charge. Now we're going to look at the potential, which is how much energy there is per unit charge. And the electric potential, so as discussed earlier, electric potential energy is not the property of a single charge alone. It depends on the value of the charges and the electric field involved. So if we vary the field strength, or if we have a charge of a greater charge or a lesser charge in terms of magnitude, then the potential energy it has also changes. So this leads us to a quantity that we call electric potential. It's given the symbol of uppercase V, and it's a measure of how much electrical potential energy is associated with a specific quantity of charge at a particular location in an electric field. So basically, it's V equals energy per charge, and it's measured in joules per coulomb. So V is the volt, and this is also called voltage, although technically it's more of an electric potential is what I'll be referring to it as. So please copy this slide down. And in terms of the note, this is also worth copying down, but please you can try to simplify it a little bit because it is quite a bit of words. So I'll just read through it quickly and then I'll make some comments. So it says electric potential is a convenient measure because it is independent of the amount of charge at a particular location in the field. It depends only on the electric field strength at that location. So for example, if you had 1 coulombs of electrons at a particular location in a uniform electric field, you would possess X joules of electric potential energy. If you double the amount of electrons to 2 coulombs at the same location, you double the amount of potential energy. So however, in both of these situations, you have the same electric potential because it's X joules over 1 coulomb or 2X joules over 2 coulombs. So it's always X joules per coulomb. This is why the voltage is an important variable and an important parameter to know. Another convenient definition relating to electric potential energy is electric potential difference. So this is delta V, and this is the change in that voltage or that potential difference between two different points, and it's the basically the change in energy from one point to another divided by the charge. Electric potential difference is the amount of work required per unit charge to move a positive charge from one point to another in the presence of an electric field. So in a uniform electric field, the equation for electric potential difference can be simplified to negative epsilon times delta D, that displacement. So please copy this slide down. Electric potential difference is the amount of work required per unit charge to move a positive charge from one point to another in the presence of an electric field. And you can copy down all of the definitions of the terms that are listed there. So rearranging for epsilon, which is the electric field intensity, we can then get the following relationship, which is epsilon is the change in the potential difference divided by the displacement. So notice that this relationship shows how a non-uniform electric field varies with the change in electric potential and the change in position in the field. So this ends up becoming another way that we can determine our epsilon. If we know the change in voltage or the voltage drop or the potential difference between 2 points, and we know the displacement, then we can also determine what the epsilon is, what the field intensity is. So according to the equation, the electric field is largest in regions where V is large. It changes rapidly with small changes in displacement. It's zeros in regions where V is constant. And it points from regions of high potential to low potential. So if we consider a circuit in which a battery is the source of electrical energy, a positive test charge will naturally move in the same direction as the electric field from the positive terminal, where a high potential exists, to a negative terminal where a low potential exists. This is what we call the conventional current. But the electrons, they will travel from a region of low potential to a region of high potential. So they actually go in the opposite direction of the electric field. That's the electron flow. So this is another example of the conventional current that's used mainly by people in the trades and in engineering, and the electron flow, which is more of the scientific physicists' look at the flow of electricity. So let's read this problem. It says the electrons in an old TV picture tube are accelerated through a potential difference of 2.5 times 10 to the 4 volts. Do electrons move from a region of high potential to a region of low potential, or vice versa? So the electrons always move from the negative to the positive. And then when it asks us next to calculate the change in the electric potential energy of the field, and it also lists that charge for an electron, which again is minus 1.6 times 10 to the negative 19 coulombs. We'll get into why that is such an important value soon. But let's look at how to solve this problem. So we're being asked to find the change in the electrical energy here. And the equation we would use, because we're given the voltage drop or the potential difference, is Q delta V. So if you remember that voltage is joules per coulomb, so if you multiply that by our charge, we'll end up with an energy. So this becomes 1.6 times 10 to the negative 19. And this is negative because it's an electron. And our voltage is 2.5 times 10 to the 4. What we end up with is 1.6 times 2.5, negative 19 and 4, those are going to combine together to become negative 15. So this becomes negative 4.0 times 10 to the negative 15, and that's joules. So let's look and see what the rest of this asks us to do. So now we are asked to find the kinetic energy. So the kinetic energy would be, we know that this is a negative. So that means that this is the energy that was lost by the field, which implies a gain of energy for the electron. So the energy is going to power up, or not power up, but increase its kinetic energy. So that means that our kinetic energy, they're saying calculate the change in kinetic energy. So we're just asked to determine the change. That's just going to be the positive 4 times 10 to the negative 15 joules. So we can use this now in conjunction with 1/2 mv squared to determine how fast the electron moves, which I think the next question is going to ask. Yeah, it says here, calculate the final speed of the electron, assuming that it had an initial speed of 0. So this is equal to 1/2 mv squared, which means v is equal to the square root of 2 ek over m, which is 2 times 4 times 10 to the negative 15 divided by m. The mass of an electron is 9.109 times 10 to the negative 31. I think they give you a different value there, but it won't matter too much when we do this. So 2 times 4 times 10 to the power of negative 15 divided by 0.109 divided by 10 to the power of negative 31. And I find the square root of this. I end up with a very fast-moving electron, 9.4 times 10 to the 7 meters per second. And that's it for this lecture. Again, if you have any questions, please post them on the class discussion board, or you can send me an email.